This is AP Calculus 5.1 using the mean value theorem. And we're going to talk about the mean value theorem and how we use it in real life problems and in graphs. The mean value theorem is very important for the AP test. They will always ask several questions on the mean value theorem, so it's one of those theorems that it's very important for you to learn. And the mean value theorem states the following. If a function f is continuous on a closed interval ab and differentiable on an open interval ab, then there exists at least one number c in the open interval ab such that f prime of c equals f of b minus f of a all over b minus a. Now there are a couple things you need to notice here. If the function is continuous on a closed interval, remember we use brackets for a closed interval, and an open interval we use parentheses. There's at least one number c in the open interval ab such that, now look at the right hand side of this function, f of b minus f of a all over b minus a. That, remember, is the formula for the average rate of change. So that's the average rate of change on the interval ab. And then this over here, f prime of c, that is the instantaneous rate of change. What they're telling us with the mean value theorem is that somewhere within the interval AB, there is a number C where the average rate of change will equal the instantaneous rate of change. And to demonstrate that, we can use a graph. If you look at this red function here, red function is your f. And we're talking about the interval from A to B. And they're saying here basically that the slope of the secant line from f of a to f of b, the slope of that secant line has to be equal to the slope of the tangent line at the x value of c. Or the slope of the secant line has to be parallel to the slope of the tangent line at your value c. And so that happens right here. You could also say that it happens somewhere I would say along here, there is going to be another value that is also parallel to your secant line. So this one happens to have two c values where your secant line is the same as the slope of the tangent line. So one of your c values would be here, another c value would be about right there. Corey lives 280 miles from a lake. He leaves his home at 8 a.m. and arrives at the lake at 12 p.m. What is the average rate of change of his distance traveled in miles per hour? What does the mean value theorem tell us about his trip? Well, if you think about that, he's been traveling for 4 hours. And he went a total of 280 miles in that 4 hours. If it took him 4 hours to travel 280 miles, wouldn't that mean that his average rate of change is 70 miles per hour? And if you think about that in real life, we know we're never going to be able to travel 4 hours at the same consistent rate of speed of 70 miles per hour. If you've ever driven on any type of road, you know that there are going to be things in your way that cause you either to speed up or to slow down. And so what the mean value theorem tells us here is that his average rate of change was 70 miles per hour. So somewhere within that trip, he probably went a few miles over the 70 miles per hour, and then he may have had to slow down at some portions of the trip and traveled below 70 miles per hour. But his average rate of speed, or the average speed that he traveled within this trip, was 70 miles per hour. Even though at some instance of time he may have traveled over or under 70 miles per hour, we know somewhere within that 4-hour trip his speed had to be 70 miles per hour exactly in order to go from a speed lower than 70 miles per hour to a speed higher than 70 miles per hour. The mean value theorem will fail if the conditions are not met. So it says for a function f, it has to be continuous on the closed interval and differentiable on the open interval AB. So I want to look at this graph here. We're going to say that our A value is at -7 and that our B value is at 7. So if you think about the slope of the secant line from -7, I would say it crosses about right here, to 7, which is about right here. If I were to draw that secant line, here's the secant line we're talking about. Now we could count the slope, rise over run, to figure out what the slope of that secant line is. And the mean value theorem says that if this function is continuous and differentiable within our interval, then there has to be a c value where the slope of the secant line is equal to the slope of the tangent line. Well, if you think about this, the conditions of the theorem are not met. F has to be continuous on the closed interval. Well, we see right here, it has a jump in the graph. It's not continuous. And then it tells us that the function has to be differentiable on the open interval. Well, if you look right here, it looks like there is a vertical tangent line in there somewhere, and it looks like it's not differentiable here at the sharp curve. So since this function is not only not continuous, but it's also not differentiable within the interval, we can't say that there's definitely going to be a number c between a and b where the instantaneous rate of change is equal to the average rate of change, or that the slope of the tangent line is equal to the slope of the secant line. Here's another example where it may not be, the mean value theorem may not be applicable. The function f has to be continuous on the closed interval ab, which in this case it is. It looks like it's closed, there are no gaps or overlaps, and differentiable on the open interval ab. Well, look right here, this function's not differentiable there, or in here somewhere we've got a vertical tangent line. So since we have a vertical tangent line here and a sharp curve here, this function is not differentiable within the interval, so the mean value theorem would not apply. For this function, on the closed interval AB, if that's A and that's B, it looks like the function is continuous, but right here it looks like we've got a sharp curve. So what that means is if this is my f of B and this is my f of A, and I draw my secant line from one to the other, and we tried to find the slope of that secant line, since there are an infinite number of tangent lines that could go through that ordered pair, and they have all different slopes, there's no way that we can say that there is one slope parallel to the slope between A and B that would be equal to that. There is an infinite number of tangent lines that we could draw here. So since this one is not differentiable at the sharp curve, the mean value theorem doesn't apply. Here's an example of the mean value theorem when given a function. Can the mean value theorem be applied to or on the closed interval from -1 to 1 for the function f of x equals x cubed minus x squared minus 2x? Now, this is a polynomial function. We know that that polynomial function is continuous based on the nature of polynomial functions. We know that this has two curves. We know that this function is going to look something like this if we graph it. We don't know how tall the maximum and minimum points are, but we do know that this is going to be the basic shape of that function. So we know it's going to be a continuous function. We also know that it's going down toward the left and up toward the right because the leading coefficient is positive. So we can say, based on our knowledge of polynomial functions, that this is continuous on the closed interval. Is it differentiable on the closed interval? Well, yes. We know that the function has this shape, and there is nowhere that that's going to have a sharp curve. So it is differentiable on the interval. So if we know that, then what we're going to do to actually perform the mean value theorem is we're going to find f of a, which would be f of -1, and we're going to find f of 1. If I plug -1 into this function, I would have 0. And if I plug 1 into this function, I would have -2. We're trying to figure out where f prime of c, or for what value of c, is the slope of the tangent line, which would be -2 minus 0 over 1 minus -1. That would be -2 over 2, or -1. So we're trying to figure out for what value of c would f prime of c be equal to -1. Well, I'm going to find f prime of x. F prime of x would be 3x squared minus 2x minus 2, and I'm going to set that function equal to my -1. that I got there. Because somewhere, if it's continuous on the closed interval and differentiable on the open interval, somewhere there has to be a function at some point c. The derivative of the function has to be equal to -1. So I'm just going to do the math by factoring here. I'm going to do 3x squared minus 2x minus 1 equals 0. And then I'm going to factor. Factors of 3 that subtract to give you 2. Well, we're going to have 3x and x. I'm going to have a 1 and a 1, and I'm going to have a minus 3x plus 1x. So my two factors are x equals -1/3 and x equals 1. So this has two c values where the instantaneous rate of change equals the average rate of change. Your c values will be -1/3 and 1. Okay, for this one, they not only give you the function, but they also give you the graph, and they ask you to determine, they say plot the line segment connecting the points on F where x equals 1 and x equals 4. All right, at x equals 1, it looks like we're about right here. At x equals 4, it looks like we're about right here. If we connect those two ordered pairs, I'm going to say it looks something like this. The slope of the secant line there is about -1. So we plotted the line segment connecting the 2 points where x equals 1 and x equals 4. Afterwards, determine all values of c which satisfy the conclusion of the mean value theorem for f on the closed interval 1 to 4. Well, the first thing we have to do is we have to look at this function, because in order for the mean value theorem to work, it has to be continuous on the closed interval, and it has to be differentiable on the open interval. Well, if you look at this function, it's not continuous. It looks like to me it's got an asymptote at x equals 0. So the function's not continuous, which means it's also not differentiable within the interval that they gave us. So we would have to say for this one that the mean value theorem, the MVT, does not apply, because the function f of x, it is not continuous on the closed interval 1 to 4, and f of x is not differentiable on the open interval 1 to 4. So there are two things that keep the mean value theorem from applying in this problem. Here, they give you a function, f of x equals x cubed plus 7x squared plus 4x minus 7. And they tell you that it's graphed. They want you to plot a line segment connecting the points on F where x equals -6 and x equals 2. Okay, so the first thing I'm going to do is plot. There's the x equals -6, and the x equals 2 is right here. So I need to plot the line that connects those 2 points. That line looks something like that. And then afterwards, determine all values of c which satisfy the conclusion of the mean value theorem for f on the closed interval -6 to 2. Well, it does look like this function is continuous from -6 to 2. It also looks to me like it is differentiable from -6 to 2. So the next thing I'm going to do is I'm going to find f of -6, and I'm going to find f of 2. And I could do that looking at the chart, but if you're not sure exactly where those things are crossing that ordered pair, they did give you the function that you could plug into. So I'm going to double check that on a calculator. F of -6 is at -5, and f of 2 is at 27. And again, I used a calculator to double check where those ordered pair y values are. And so the next thing I'm going to do is I'm going to find the difference quotient, or the average rate of change. So I would say 27 minus -5 is +5, over 2 minus -6 is +6, and that gives me a 32 over 8. And 32 divided by 8 is 4. So the average rate of change here is 4. So I need to figure out the c values where f prime of x is equal to 4. So f prime of x is 3x squared plus 14x plus 4. And I need to set that equal to 4. So 4 equals 3x squared plus 14x plus 4. And if I subtract the 4 over, 0 equals 3x squared plus 14x. And I could factor that. When I bring out an x, I have 3x plus 14 left. And so this would happen when x equals 0, and it would happen when x equals negative 14 thirds. So my C values here are x equals 0 and x equals negative 14 thirds. So my C values here, where the slope of the tangent line equals the slope of the secant line, happen at x equals 0, so right around here, and at x equals negative 14 thirds, which is negative, I believe, 4 2/3. So somewhere right in here, I would say. The last example, it says selected values of the function f are shown in the table below. The function f is continuous on the closed interval 3 to 5 and differentiable on the open interval 3 to 5. Determine the validity of the following statement. There exists a value c in the open interval 3 to 5 such that f prime of c is equal to 4. Well, this one's a little bit different because normally we're talking about the interval from 3 to 5, and if we did that, we would be talking about -1 minus -6, which would be 5, over 5 minus 3, which would be 2. So the slope of the tangent line they'd be talking about is 5/2. But look what they gave us here. They said f prime of c equals 4. Okay? So if you think about that, they're not necessarily going to use the two endpoints here. It looks to me like they're using these two endpoints. So we're using the points 4, -5 and 5, -1 to show that f prime of c equals 4. Now, if this function is continuous from 3 to 5 and differentiable from 3 to 5, doesn't that mean it's also continuous from 4 to 5? And differentiable from 4 to 5, that 4 to 5 is within the interval they talked about in the beginning of the problem. So we know it's differentiable and continuous for these 2 points. So if I find f prime of c here, -1 minus -5 would be 4, and then 5 minus 4 is 1, that equals 4. The mean value theorem does apply with a portion of the total interval that they're talking about. They just happen to be talking about just part of the interval in the original problem. So we know that f prime of c equals 4 from 4 to 5, so that statement must be true based on the mean value theorem.